So today we're going to do the test 3 wrapper problem number 2. And in this problem it says we have a conveyor belt that carries electrons from the left to the right a short distance s from a very large metal plate to another large metal plate. So there's a constant force, which is a non-coulombic force, acting on this one electron. And there's a negligible friction in the conveyor belt. And thin nichrome wires and thick nichrome wires are connected to the plates as shown. The thick wires have a length of L1 and L3 and the same diameter D1. And the thin wires have length L2, which is equal to L3, and they have a diameter of D2. So we're given that the L1, L2, 3, and the D1, D2 have these relationships. And what the first question we state is we have to determine we have to draw the electric field at the locations X as shown above, and I drew the X's and I went ahead and drew the fields too, and show the approximate charge distribution everywhere else. And we have to be careful with the relative magnitudes of the electric field as well as the correct directions. Okay, so what you have to do with this problem is you have to notice that the electron's going from here to here, so that means this plate's going to be negative because that's where the electrons are headed. And leaving, since a lack of electrons, this will be positive. So this is why the first electric field, there's a large one that points out because you not only have the electric field from the negative that points in this way, you also have the positive going from the positive, so that's like a double whammy. And we know since electrons are moving this way, because that's the way the electron arrow is pointing, we know that the conventional current has to flow the opposite way, because the opposite of electron current is the conventional current in direction. So that's why we know that our electric fields have to point in that direction. As far as magnitudes go, the electric field in the smaller radius has to be larger because of the node rule, which says the I thick has to equal I thin. So, that's how it is. So with that, we know that the electric field in a thick wire has to be a lot larger, because if you decrease A, which is the cross-sectional area, and you still want them to be equal, you have to increase something else on the other side. Or you have to increase something else on like the same side. So that's why you have to increase E. As for the charge distribution, they have to think of these as like a positive zone and a negative zone. So the positives are going to go out, but as you get farther and farther from like the source of the positives, you're going to get less, and the same goes to the negatives. So the next question asks us to calculate the magnitude of the electric field at the point A, B, C, and D. And I so helpfully labeled and circled each one. So, of course, let's do the easy one first. The electric field at B is equal to the electric field at C. This is because of the node rule, so that the I in has to equal the I out. They both have the same thickness, and the same material, so therefore they will be the same. Where the electric field starts to change is in D here, because you're making a thinner wire. So how I like to tackle these problems is I like to write every living equation I can think of. So I started out with the no rule, saying that the I of the thick, so at C and B for that matter, has to equal D. So I did my equations, and using these things that they gave us in the problem, I knew the relationship between L3 and the D's. Note that I did use D squared, even though it probably should be an R squared, but since they canceled out, I was lazy and I just wrote D anyway. And the 4's would cancel for that matter too, and so would the pi's. So that leaves us to EB is equal to 1/9 ED. So that's what we have there. And from there, we use our loop rule, which we know how to write. Because you first go from here, that's your EBL1, and then you do your, and then you go, this is how you start, and then you write your loop rule, and you go from the start, and you keep on going around until, we know that delta V is equal to EL. So every time the electric field changes, or then, or L changes, you have to change your loop rule equation. Or you have to add a new part, because that adds another delta V. There's a different change in potential for that one. So what I did was I pretty much, from once I got like the initial node rule equation, what I did was, or loop rule equation, what I did was I first condensed it because I knew I had EBL1 here. I knew I had another EBL1 going out. So here, actually, there's an EB1 here and then one there. So I knew I had those two. And I had the EBL3. Well, L3 is different, but the E is the same, so I can combine them. And then I had the small d's, which I also combined and got this equation. And from there, I used this formula to relate L1 to L3 and L2 to L1 so that I can write in a single variable, or start to write in a single variable. And then after that is I just combined them together after I did that. And now I have this equation, but I already do know a formula that I solved earlier that relates EB and ED. So I plug that in, and this is what I get after I plug and chug. And I knew that EA, which we solved at the beginning, we solved that, we know that EA is equal to the force non-Coulombic over the charge of an electron, because the EMF, or the delta V, is equal to FNC times S over E, which is equal to delta V, which is EL. But in this case, we're calling it ES because that's what the problem called it. And that's how we got this answer. The S's cancel out. And we know that's how we got what EMF was. So from that, we just put this back in here to get these final answers. And that is how you do the problem.